this dimensionless Marangoni stress, and we saw that I could arrange it into some factors that went as ultimately as, let's say, 1 over mu u, some derivative of the tension with respect to its composition and a change in composition. And I had then, coming out of that, some prefactor information, something that depended upon the composition, and the characteristic difference in concentrations that I could get by balancing, for example, surface convective fluxes against adsorption and desorption, or surface convective fluxes against diffusion. And I saw I had these limits, that if I looked at that delta gamma at large concentrations for adsorption, desorption controlled systems, that my Marangoni stress approached a constant. So I couldn't restore free motion. But if I looked at high concentrations for this delta gamma for adsorption, for diffusion control, that length scale, h equal gamma equilibrium over C infinity, appears in my delta gamma. And it lets us slide on to this inability to dilute the bulk. And so we can have very rapid diffusional fluxes to and from the interface. And we can restore free motion. And I wanted to say just a moment why, before we continue, why that was interesting, really. So that was interesting because this factor here is quite large typically. This is an elasticity number divided by a capillary number. Capillary numbers are typically very big numbers, or very small numbers. So it's very different. You know, if you think about it's a normalization. A capillary number is a normalization between your velocity of your prevailing flow compared to the characteristic velocity for a surface tension-driven snap-off. Okay, so these are capillary numbers are typically very small. And so this prefactor here can be big, can be easily order of tens, if not larger, in many systems. Okay, and so, I'm supposed to wear the, I hate these things. I don't know if you noticed me limping while I was wearing it. Because I didn't wear my boots to put them in. Now can you hear me? You could hear me before? Is it on? Okay, did you guys know about mentoring and career guidance? This is mentoring. I have a female colleague that taught me what to do with a microphone when you don't have pockets. Okay? Okay. So this prefactor is typically tens, if not larger. So the idea that you're going to start with some system and say, I have some prefactor that couples the stresses to the composition. That's very large. The idea that this would go small, that this product would go small enough to let me have restored motion was a surprise. Okay? So, so on spherical drops, I took you through this scenario where we can go from a stagnant cap limit, and then if mass transfer is a little bit faster, all the drop participates and the surface velocity is retarded uniformly but not zero, right? And then if mass transfer is fast enough and really fast compared to convective scales, we don't get barriers at all, right? And we saw that we could get that very easily with the diffusion by going to high concentration. And for adsorption, desorption, if I fixed my BO number fixed, I could not really restore free motion. There was always some limit. Okay. And the scenario I really want to, and now we're going to switch to just thinking about, okay. And we had started the whole discussion with thinking about this limit. Looking at this limit where we said, what if exchange was just really slow? I started with that one, right? And that was the one that gave us stagnant caps. And then I went through this entire scenario about if we're soluble, what can we do that's interesting? Okay. But now, I'm just going to return us to thinking about stagnant caps. Let's go back to that, okay? Where we saw at steady state on that non-deforming droplet that was translating at some steady velocity, that at steady state, we had regions of the interface that were stagnant, and they had surfactant, right? Convection swept things to the back, and if there were surfactants there, the velocity was zero, and everywhere else we were mobile. And now let's think about what happens for a drop that has leading order deformation. So let's suppose we think about a drop that's in Taylor's extensional flow at Cambridge University. Okay, so let's start with a drop that's centered in some flow field that applies some rate of strain to give a pure extensional flow. Okay, and we start with a spherical drop, and it's going to have some surfactants on the interface, and those are not soluble in solution. We're just going to say it's like one of those experiments where the drop sat there overnight, things came on to the interface, then we run an experiment by turning on the 4-roll mill apparatus, and molecules don't have time to come and go from the interface compared to the time scale of the experiment. Okay? And we're just going to start thinking about what happens if we change the fractional coverage of surfactant on the interface. So surface concentration over the maximum packing. Okay? And so again, we'll go back. We have our jump in stresses at the interface are given by where this is the total stress tensor now, a jump in the mean curvature times the interfacial tension, and there's a Marangoni effect. And we have this elasticity number over the capillary number, characterizing this prefactor that we derived previously. And we're going to ask ourselves, how do surfactants on this droplet change its deformation at steady state? We'll start with that question. And I was trying to list people who had done work here, and there's been beautiful work done here. So this is not an exhaustive list. But I will brag that I did my postdoc with Barthez Bizel and my PhD in an institute run by Akrivos. And Petya Vlahovska is someone I love and admire, and who doesn't know Howard and Gary? Do you guys know them yet? You will. Okay. So this is a profile in which there's been a lot of beautiful work, and I'm going to just focus selfishly on stuff I've done and then allude to their work periodically. Okay. So going back to our model of the nonlinear surface tension model, if I look at my surface tension and normalize it with some reference value, I can define my elasticity number. And if I look at derivatives in my surface tension, I can get this first order pole. And this elasticity number, a very typical value, could be on the order of 0.1 or 0.2. Okay, so this was not, let me go back one. I'm talking about my Marangoni stresses here, and throughout, I'm going to talk about this parameter and talk about the capillary number as a separate beast. We're going to just factor it out. It will be there, okay? But my effective Marangoni number is going to be elasticity number over capillary number, and I'm going to look at this flow field as a function of capillary number. So I'll start from small capillary numbers, let the drop come to some steady state, tell you about its deformation, augment the capillary number, let it come to some steady state, talk about the deformation, etc. And so the capillary number will be explicit in the formulation. So I'm just going to focus on this elasticity number for now. RT gamma infinity for a typical cross-sectional area of a molecule, 1 over cross-sectional area put in here for gamma infinity, would be on the order of 0.1 or 0.2 for many common systems. Okay. So then using our nonlinear law, we have here that our Marangoni stress is going to be proportional to the product E, that number that was less than 1, X, my fractional coverage, divided by 1 minus X gamma. So here's that pole that I have as I start to approach it. Okay. And so X is my fractional coverage. So if I look at a really dilute coverage of surfactant, then, and I'm starting with a system where I'm not allowing adsorption-desorption exchange, then if X is much less than 1, this piece is negligible. And del S gamma, when I just start this flow with a dilute amount of surfactant, is going to go as 0.2 times something much less than 1 times del S gamma. The drop couldn't care. So we can just, the surface velocities can proceed unimpeded over most of the initial behaviors of that droplet until I start to accumulate something in the pole. So for this case, starting with a low amount of surfactant, I should expect a sweeping toward the poles. Okay, so at steady state, I should expect significant accumulation near the poles and depletion near the equator. In contrast, if I start with a lot of surfactant on the interface, so I'm very close to maximum packing, then this is a number 0.2 times 1 divided by a small number. So in this case,
we should expect very strong coupling from the beginning. And so any attempt to redistribute that surfactant is being fought by this term, which is becoming quite large. And so that's going to say, please dilute at nearly uniform concentrations. And so if you started your experiment and you'd done something to measure your surface tension, and you thought you had some value, okay, that you have an apparent value of surface tension, this system, we should expect that it's going to dilute as we expand. I'm looking at an insoluble surfactant, nothing being supplied from the bulk. It starts to extend, but it's extending in a system where the surface, the Marangoni stress is saying, please don't create a gradient. Okay, so we should expect very different outcomes from dilute systems versus concentrated systems. Okay. So again, I told you I want to focus just on this case of an insoluble surfactant. So our surface mass balance takes this form. My rate of change of the surfactant concentration has some surface convective term that I've broken out here to be explicitly the tangential piece. Some other piece that comes from the stretching of the interface. So both of these come from a del S dot gamma surface velocity that contains both normal and tangential parts. Okay, these together are the surface convection terms. And in addition, we have diffusivity along the surface. And I'm going to keep this small but finite. And again, I'm going to factor out the capillary number to keep it explicit. We're going to say, let's fix all of our physical chemistry by fixing this parameter lambda, which is the Peckley number divided by the capillary number, and fix the elasticity. And we're going to vary the capillary number over some range and the fractional coverage of surfactant, and just look. But you already have instincts for what this is going to do at steady state. So at steady state, this goes to 0. At steady state, my droplet stops deforming. I have some weak surface diffusivity, and you can see hiding in here is everything we did with that divergence. Okay, so let's start going through. So the way that these little simulations were done is we start with a droplet that's spherical, and we know the stress jump on that droplet and plug it in here. This is a Green's function, axisymmetric Green's function for the droplet. And by putting in the stress here, we can calculate the velocity along the surface. We use that velocity to update the interface deformation, to redistribute the surfactant, and update the stress condition, put the stress condition in here, calculate the velocity. And so this is this time marching scheme to go forward and to calculate the shapes as you approach equilibrium, steady state. As you approach steady state, or to show your steady distributions. So first for dilute systems. For dilute systems, as I said, our initial Marangoni stresses are very weakly coupled. And so surfactant present on the droplet in this extensional flow that moves us from the equator towards the poles can allow the surfactant to be swept clean from the equator and accumulate in the region of the poles. And so at steady state, we have exactly what we had on these spheres, right? We have swept the region of the equator clear of surfactant and accumulation near the poles. Okay. As we add more surfactant, that region with accumulation, so here's surfactant free, here's a region of accumulation. As we add more surfactant, the Marangoni stresses become more pronounced and then eventually uniformly distributed over the droplet. So this is going from a fractional coverage of very low to 0.5. And so here again is the clean deformation. This is the Barthes-Bizel's version of the Rallison and Acrobos result. It's her asymptotic expansions. And if we look at what happens as we add surfactant, the deformation increases with added surfactant. And so we now have instincts for this. This is nothing but this argument of being able to have regions swept clean and regions that are surfactant populated. And so we expect to see what we saw previously, and I've got the approximate here because I kept a weak surface diffusion. And so it's not a complete equality. So I expect to have some mobility in the regions that we were stagnant before. So again, this is the equator, that's the pole. And we see that we have regions of mobility and regions of strongly reduced mobility, and that this grows as we increase the coverage to cover the drops. Let me do that again. Here's the clean interface. Small amounts start to decrease the mobility, and then at higher coverage completely quench the mobility, except for the small amount that's allowed, because this is actually not quite zero. It's balanced by the weak surface diffusive flux. And again, the surface concentrations, where the surface concentration is finite, the surface velocity is zero. Where the surface concentration is zero, the surface velocity is pronounced. So this is just the tangential stress limit that was the stagnant cap limit, but now on the deforming droplet. And it says dilute surfactants, where we're weakly coupled, can increase the deformation of the droplet. And as we've already anticipated, it's all going to turn around. That if we go to the nonlinear law, then our initial gradients are very pronounced. And the closer we get to 1, the weaker the surface concentration gradients become. And so here, starting from 0.5 and increasing to above 0.99, we see the surface concentration becomes essentially uniform over the surface of the drop. And that drop is diluting because the tension's staying essentially uniform, because the concentration is staying essentially uniform, but the tension isn't. The tension is varying strongly over the surface of that drop. This is diverging, and very weak gradients here with this factor are giving a finite Marangoni stress. And so we see by increasing the amount of surfactant present, we go from being more highly deformed than the surfactant-free case to having a lower deformation as we dilute. And here I just wanted to comment on this behavior. What we've done here is I'm at a capillary number for this case that's 0.05. So E over Ca, which is my Marangoni number, is 4. It's order 1. This prefactor, which is how sensitive am I to tension, normalized by now my viscous stresses, is order 1. And this factor goes for x of 0.1 from 0.4 to 36. So we're increasing this coupling by orders of magnitude by changing the surface coverage. And you can go to higher surface coverages clearly and get this to be higher. And all we're doing here is we're seeing that because of the nonlinearity of the coupling of tension to concentration, this term's divergence is forcing us to have a finite Marangoni stress, which is starting to superpose at high coverages, that's forcing the surface concentration to remain uniform. It's a 2D incompressibility. Surface tensions are related to surface pressure, right? Surface pressure is the reduction in surface tension. Here, by being highly coupled to changes in composition, we're exploring some region of extremely steep change of our pressure isotherm, and the system is forcing us to remain uniformly packed on the interface. So the Marangoni stress is becoming whatever it has to be to enforce that uniform packing. And here, just to show other results along these lines, here's the surface concentration as a function of arc length as we became to greater and greater surface coverages, and it becomes essentially uniform. This is my surface concentration normalized by the maximum packing, and we can see as we approach 1 that the concentration gradients become extremely weak, but the surface tension is non-uniform. So what happens if we vary time? That's okay at steady state. At steady state, we look at the system and I say, what's your Marangoni stress? And the Marangoni stress says, I have a prefactor in front of the surface concentration gradient that's really big. And you have an external flow, and the flow is occurring. Everybody has to remain finite. We say, put the surface concentration gradient to 0. But while you're dynamically evolving your shape, you're not incompressible. Your drop is going to go from some shape and stretch to be some other shape. Right? So in that case, the Marangoni stress is still there. It's saying, do whatever you have to do to keep the surface concentration uniform. That divergence keeps the surface concentration uniform. And so if we look then at our surface mass balance, and I neglect anything that has to do with being spatially non-uniform, say my surface concentration is essentially a constant, and I factor it out, my surface mass balance takes this term. And if I'm an insoluble surfactant whose concentration is staying uniform, this is ultimately an argument about the area dilatation. And it says something reassuring, that in this limit, the rate of area dilatation is given by del S dot ds. So this is what happens for a deforming drop that's in this highly coupled limit, that these are unreadable even by me, that the normal velocities and tangential velocities balance each other, that there are two flux terms, that the tangential terms and the normal terms balance each other so that if there's, for example, a stretching at some location, there's an inflow to keep the concentration uniform. Okay. And so this is this concept of a 2D incompressible layer, but for a surface that can be extended or compressed. Make sense? Okay. So this is a limit that's often invoked, and it's often invoked by saying this prefactor is big. Okay. And then it's not a whole lot of context in saying much about the compositional pieces. And so if your prefactor there was really, really big, your elasticity number over Ca, it was big enough that that dilute regime still puts you at a very highly coupled system, then it's universally so. But if you're dialing through these different behaviors, you have to expect a change of behavior from being a system that can be redistributed very easily to one that cannot be redistributed easily. And so but it's a wonderful starting point for many systems. And so it's very commonly invoked in many excellent papers on trying to understand other issues to do with interfaces. They say, let's begin a priori by assuming a two-dimensional incompressible layer. And you just want to be aware of pitfalls while you're assuming it. Okay, so so there was this observation done near here many years ago of a droplet that was in the 4-roll mill apparatus and that shed small droplets. That this 4-roll mill apparatus was turned on and the droplet pulled out some little thread and shot out baby droplets. And the baby droplets, their length scale didn't make sense with the geometric length scales of the system or with any obvious a priori argument you might make about arguing for their length scale. They were the wrong length scale for example, a Rayleigh plateau breakup. And so, so for many years, the concept of that this was created by some dilute amount of surfactants had been played with, but we were able to simulate this some years ago. And so here is a drop with, I think, a fractional coverage of 0.1. And it's the same simulation where we said, turn on the capillary number, let the drop come to steady state, report a deformation. Up the capillary number, report the deformation. And then you up the capillary number a little bit more, and there's no stable shape. And so these sorts of calculations were done by Stone and Leal, for example, absent surfactants, to look at all the beautiful different breakup modes that viscous drops can do. This is done with a drop whose internal viscosity is 0.1 the external viscosity. So let's see if it'll play. And so the whole point here is that here we see a cap. And if we were if we're at steady state, this would be a stagnant cap, but we're not at steady state. The flow field is pulling this way. The surface concentration is the surfactant is becoming compacted toward this pole. The surface tension drops as the concentration approaches maximum packing. That requires a higher curvature in the region of the tip. And so we'll just watch this drop evolve. I think it slows down because we took little time steps, not to give you. And so you can see to the resolution that we could do at that time that this is pulling off baby droplets. And so the length scale of that thread is associated with not just the scale of this cap, but the zone where the capillary number became small, where the zone where the surface tension, let me be careful, became small, where the small enough that the capillary number became order 1 and was able to pull off this thread. And so this was this conspiracy of the surface tension law and the strength of the external flow, and the fact that we were a surfactant that could not easily pop off the interface and diffuse away, that this was a surfactant that was trapped on the interface over the timescales of this system. And so if we look at low coverages, we could see pulling out of these small threads. And if we look at larger coverages, you can see the entire parent drop participates and pulls out to participate in that breakup mode. So there's very beautiful work done on this in many years since. So here's work in a flow focusing device, where a droplet is put in a flow focusing device. There's a flow that's feeding this liquid in, and there's an external flow pulling around here, creating a local extensional flow. And you can see here our breakoff of droplets on a scale that looks like it's akin to that of the geometry. Here we can see suddenly this emergence of some other length scale. So this is just increasing the velocity of the flow. Were these all movies, they'd be playing for you, but I think that this is the only movie I managed to get from Shelley Anna years ago. So I'm going to show you that movie now. You see this droplet, and it's a low viscosity droplet compared to the external phase, and you see it shedding these baby drops, and did you see it spits? It goes, it runs out. And then after some time period, it starts again. And so that sputtering, we think, is because it's being stripped of adsorbed surfactant and it's taking time to replenish the surface. So there's recent work that I'm still working to understand, but I want to tell you about it. It's not fair not to share it just because I don't understand everything it implies about what I'm saying today. But it's work done by my former colleague, Andrea Prosperetti, and he was thinking about how could we unify thinking about tip streaming, about droplets that when they rise at finite Reynolds numbers can shed skirts behind them, about coaxial jets, and about filaments that happen behind very low interface tension oil drops. And his thinking is that we can unify all of these by recognizing what I would say is that, what I've said in the past was that here's a point in the flow to which the surface velocity converges. And that converging surface velocity can cause surfactants to accumulate here. What Andrea says is that we can think about this more generally. This is a point of zero vorticity in the flow field, and that disturbances along the interface can be convected to this point and then become unstable and be pulled out by this extensional flow that's adjacent to that drop, that location. And so, so the argument that he would propose is that surfactants help this instability, but this instability does not require having surfactants present. He's in his JFM paper that I have references that I'll share with all of you. He's done simulations near various locations of zero vorticity with a converging surface flow, and talked about the instability in the context of that mechanism. And then I wanted to show another example of a phenomenon that one is related to what I've discussed. It's different, but it's related, and another maybe not. So it's about putting a droplet in some electric field, and under the leaky dielectric model, depending upon the ratio of conductivity ratios and permittivity ratios, in some cases we'll polarize with the charge accumulation positive moving along with the field and negative against it, and you'll end up with a prolate with a dipole facing this way, and in the other limit you'll end up with a dipole facing that way. And associated with those are flows, and the flow for this case gives a flow that converges toward the poles, and the flow in this case gives a flow that converges to the equator. So first let's focus on this one, which is where the flow converges toward the poles. And so there's some compression of charge that can happen. And you can think about a mass balance now of charge along the interface with fluxes coming from the electric fields as well as from the flow. And so this is work that Petya Vlahovska gave me this week at Northwestern, where I gave a talk on Thursday. And you can see her very beautiful experiments of tip streaming and then subsequent relaxation when things have been shed. Okay. And here's the other example. And what makes it tricky is that this flow is converging here to this point where the negative charges and positive charges meet, and we shouldn't expect an accumulation of charge there. And so what she sees, here's a side view. Can you see? The drop is shedding this beautiful Saturns. Do you see that? That skirt comes out. Here's the top view. It doesn't sputter, it just goes and goes and goes. And this is again looking up close at the rim of the droplet, shedding those skirts. Those are open issues. All right, so I wanted to close by saying I talked about how a piece of the story about interfaces that we think we understand, this business of transport and selecting regimes for this class of surfactants that obey local equilibrium, that don't have adsorption, desorption barriers, that don't have viscosities, etc. Okay, and there's so much more that happens at interfaces, so I just wanted to show you just a handful of movies. One thing that interfaces will do is they'll accumulate stuff. Did you guys ever make hot chocolate with milk? Did you ever heat the milk? Isn't that disgusting? Okay, so the skin that forms on the milk forms on a whole bunch of other interfaces. So here's just work from my lab. There's beautiful work going on in Edinburgh of absorbing proteins that are making some thin solid film that undergoes some wrinkling under some bending modulus that's supported by that film. This is no longer a fluid, it's skin. Okay? This particular skin was made by, I have two different movies. One is polyelectrolytes absorbing from one phase to the other and forming a two-dimensional membrane. This one is a film that's made by bacteria that adsorbed to the interface and secreted polysaccharides and other materials and made a skin. So that thing isn't even a fluid anymore. So you can talk about the tension in that skin, but it's not an interfacial tension. Okay, so there's an example of interesting systems that happen. Here is a thin, solid film that was made by having a bunch of gold nanoparticles on a particular interface, and the fluid was squeezed out of that droplet, and boom, they fell into some van der Waals well and made a membrane. Also a thin, solid sheet. These are a film on a pendant drop of adsorbed nanoparticles, gold nanoparticles, but they had enough surfactant on them that when they got squeezed together, they formed a fluid layer. And that fluid layer remained fluid as we squeezed the droplet. And those particles, as you squeeze and squeeze and squeeze, they popped out of the interface. And that if I gave this thing time, and I'm too impatient to do it, that is a sedimenting cloud of nanoparticles that were squeezed out of that interface. So depending upon how you treat the materials, you can go everywhere from having, and the host fluids. The oil was also special in this case. It allowed those surfactants that were absorbed on the surface to remain fluid and extended. And then here's an example of ongoing work in my lab, and if it makes your skin crawl, it should. So those are Pseudomonas bacteria at oil-water interfaces. And so it's just another example of things that will accumulate in interfaces and undergo interesting dynamics. So the field is moving fast. There are many, many different phenomena that occur at these fluid boundaries. And I really chose today to tell you about the simplest system that for which we have a fairly complete story that allows us to turn knobs. And so with that, I'll conclude.
Some question, please.
What is the typical size of these ejected droplets? How does it depend on any concrete length scales?
Yeah, yeah. So, so I wish I in fact do not remember exactly for this one, but I think this ratio of droplet, we could think about this in dimensional terms as being a droplet of, say, a couple of millimeters in diameter, okay, for a typical length scale. But in Sheliana's experiments, they were a couple of 100 microns. But her system differed also because those were very soluble surfactants, and so there might have been adsorption to the surface over the course of the experiment. So let me put up her experiments to show you that experimental realization. So hundreds of microns. So it's almost a millimeter, the width of the upper channel. And the gap here is 280 microns, is the water drop opening.
That's what you see, but there might be something that is even smaller that you simply optically do not see.
That's right. But if you're looking for, yes, I think that that is possible. There are ways surfactants make teeny, tiny droplets, but it's all thermodynamic and not what I'm talking about today. But if you want a trick to get to teeny, tiny droplets, I can tell you.
Tell me now.
Microemulsions.
Another question. With respect to like the tip streaming and that example that you showed with the gold nanoparticles, would you expect normally that the majority of the expelled material would be the surfactants, or would it sometimes bring along with it the host material in like a trapped state?
Oh, it definitely has host material. Like the droplet's made of something. So the volume of the drop is well, in these approximations that I've done, I used Gibbs approximations and assumed a two-dimensional dividing surface and a zero thickness interface. So all of the droplets were very large compared to the scale of a transition across an interface. And so for those cases, the drop volume is all made up of the host of the fluid. And so certainly I think that would be an okay assumption in these experiments, for example. So every droplet that you see is bringing volume material with it and forming interface as it's formed. So that's the magic of a fluid interface, right? That it just gets formed when the droplet forms. The interfacial area is spontaneously formed. But yeah, there's bulk material.
I have one question. So this tip streaming which you showed, right? So can one create more tips or different tips, say by having a structure inside the droplet? And I know that people in the audience would do also liquid crystals and others, right? Could you use some inner property, inner structure of the droplet to?
I know that people have done tip streaming with nanoparticle laden droplets. I think Rothstein at UMass showed tip streaming using nanoparticles as surfactants. So there's an example. But I think that the questions about, and there's a literature there, but the questions about how to use liquid crystals to do clever things in forming structures, I think is a very interesting question. Whether, how would the anisotropy of the host fluid couple to the interfacial tension to give you interesting effects? Certainly there's been a lot of work done, a tremendous amount of work done on particle-laden droplets and very interesting anomalous stress behaviors that are not because of surface tension, but because you can form two-dimensional solids. But within this fluid interface region still, I think that there's work to do with surfactants and liquid crystals that could be interesting, yeah.
I have
a second, if I may, right? So because I know
I
that
stunned you.
I know roughly the background from the audience, right? So what I mean today, activity is a phenomenon which is strongly explored in various contexts. And what is how would you talk about it in the context of surface phenomena?
Active things, you mean?
Pardon?
Activity in what sense?
Activity. I mean, there's
Things that fuel themselves
yeah,
and
so
move.
you have active agents, active
Yeah.
objects, bacteria, filaments.
Yeah. So
surfaces.
yeah, we're working on that, and so we're very early stages. And so I'll show that movie again, and so every little black spot is a bacterium, and whenever they go gray, it means they've left the interfacial region. So typically you would expect a microscale object to hit a fluid interface, make a hole in the interface and become trapped. And we have a bunch of guys that seem to be able to, leave and come back. We see all these near particle interactions, but we actually we're looking right now to see whether we can understand the hydrodynamic interactions in these layers. These guys, they stay so busy. They're not restructuring the interface. We found some conditions in which we could grow them, in which they were not secreting the polysaccharides and not making that skin, that two-dimensional skin. And so we can remain active for a long period of time. And so we're just trying to understand, first of all, thinking about what are the hydrodynamic singularities and how to derive them for something that's stuck at a viscous-viscous interface, close to the interface. Not using a far field approximation, and then trying to understand what are the interactions, and we have experiments going on to try to understand how can they come and go. But I think ultimately I think that there's a very nice vision that was put forth by Kyle Bishop at Colorado in a current opinion of colloid interface sciences, which is we so often talk about active objects as microrobots. But there's sort of this vision of going back to surface active materials, but instead of thinking about a surfactant, think about an active material. What does it mean if you can imbue your boundaries with dynamics, and how might you exploit those if they would self-assemble and make a structure? So these are really at very early days, all of this. It's just become a well-behaved enough system for us to actually do any science with it. But that's the vision. That's the vision, is to think about, can you absorb structures that either that they do form some sort of coherent or interacting structure, or if these are somehow truncated in their range of interaction, to exploit that. Yeah.
Are these flagellated?
Yeah, it's PA14s.
They're swimming close to the
Yeah.
interface in water.
Oil water. Hexadecane on top. Yeah.
Okay. So if there are no more questions, let us thank Professor Stebe again, and thank you, Professor Stebe.